Hi there, Dr. Steve Kuczynski back again, and this is a video in response to a comment that was made on my Mohr circle in Excel video. Someone said, can you make the von Mises ellipse in Excel? And I said to myself, well, sure I can. Then I sat down to do it, and I realized it was a little more subtle, and there was a little bit more going on than it first seemed. So, got very interesting. So one, thanks for the comment, thanks for the idea. Two, let's see how we do it, okay? You'll notice I'm not in Excel right now, though. That's because I want to go through a little bit of how I got to where I made my Excel, right? What steps I went through to make this happen. So the first thing is, of course, here's the von Mises ellipse drawn on the left side of the screen here. Hopefully you can see the mouse pointer, right? So what's going to happen then is we know this ellipse crosses the axes at plus or minus sy, doesn't matter where you're looking. And we also know that this ellipse is tilted at an angle from the sigma 1, sigma 2 axes. Again, sigma 1, sigma 2, as usual, are principal stresses inside in some plane, where the third direction, sigma 3, is assumed to be 0. We assume plane stress, right? And these are the various values of principal stress that we can have in the plane that define where failure occurs. Inside the ellipse is safe, outside is yielded, on is the line between safe and yielded, right? So what we can do then is recall, first of all, that the equation of this ellipse is that the von Mises stress, sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared, is equal to the yield strength. And that has to be to the 1/2 power. It's the square root of all that stuff squared. Otherwise, the units don't work, right? And some things we have to remember about this ellipse are, first of all, that it's tilted, as I've drawn it, at 45 degrees. And again, this angle in here on the left, also 45 degrees. And we have to remember an ellipse is defined by its major and minor axes, right? Or in this case, the semi-major axis, little a, the distance from the center out to the most extreme point in one direction, in the long direction in this case, and little b, the semi-minor axis, okay? So if we can get those distances a and b, we're fine. How we do that comes back to the fact that we know it's a 45-degree rotation. So if we know it's a 45-degree rotation, this intersection point here must have sigma 1 equal to sigma 2. Okay. This intercept here, 45 degrees again, except now I'm going to the left from the origin as opposed to from the right as I was on the first one. That means that sigma 2 here is equal to minus sigma 1. Essentially, these are like the lines y equals x and y equals negative x. So now if I want to get a and b, I can do that by figuring out what sigma 1 and sigma 2 are, right? Now, at those 2 points, I should say. So at the left-hand point, if sigma 1 equals sigma 2, the equation for the von Mises ellipse becomes sigma 1 squared minus sigma 1 times sigma 1 plus sigma 1 squared all to the 1/2 is equal to yield strength. And I hope you'll agree that this center term becomes negative sigma 1 squared, so two of these get knocked out. And what we wind up with is the very simple sigma 1 equals sy. So therefore, a has to be equal to the square root of the sigma 1 coordinate squared plus the sigma 2 coordinate squared, right? A is equal to square root sigma 1 squared plus sigma 2 squared is equal to square root of sigma 1, actually not even sigma 1, pardon me for a sec. Sigma 1 equals sigma 2 equals sy, so yield strength squared plus yield strength squared, again, because sigma 1 equals sy and sigma 1 equals sigma 2, right? That a coordinate has to be root 2 sy. That semi-major axis is root 2 times the yield strength. Okay. What if sigma 2 equals minus sigma 1? What about that case? Well, then the von Mises equation becomes sigma 1 squared minus sigma 1 times negative sigma 1 plus negative sigma 1 squared to the 1/2, which is equal to Well, that middle term just turns into sigma 1 squared, and the end term just turns into sigma 1 squared. Hello. So really what I wind up with is root 3 sigma 1, and that has to equal the yield strength. So it looks like sigma 1 is equal to 1 over root 3 times the yield strength. And since sigma 1 equals negative sigma 2, to get little b, it's going to be equal again the square root of sigma 1 squared plus sigma 2 squared, which is equal to the square root of yield strength over root 3 squared plus negative yield strength over root 3 squared is equal to root 2 over root 3 times yield strength. So these two things here, this root 2 sy and this root 2 over root 3 sy, those are going to be our tickets once we figure out how to make the ellipse. Because now we got to make an ellipse. And making an ellipse this way, aligned with the x prime, I'm calling them, and y prime axes, we'll get to x and y in a minute, that's easy, right? If I have an angle theta, it's a parametric angle, so to speak, what we can say is x prime is equal to a times the cosine of theta, where a is the semi-major axis. Hey, that's our root 2 sy, that's why I bothered, right? And y prime is equal to b sine of theta. Well, hey, look, b is just root 2 over root 3 sy. Again, that's why I bothered, right? That gets us partway there. That gets us an ellipse, which will look like the von Mises ellipse, except not tilted. But we probably want it to be tilted. We probably want it to look right, right? And also, we want to know we can get it correct by seeing that it crosses at the yield strength. Okay, well, how do we get it to rotate? Well, what we do then is we execute what's called a coordinate rotation, okay? We're going from this x prime, y prime coordinate. This is where the ellipse lives. If I set up my x prime, y prime, I use those equations I just pulled up, scrolling back up for a sec. This x prime is a cosine theta, y prime is b sine theta, make the ellipse every time, right? So how do I make that into x and y? It turns out that x is equal to x prime times the cosine of 45 degrees minus, that's a minus, right? And this is just a standard rotational transformation. If you've seen this in like a dynamics course or something, that's all I'm doing, right? Y prime sine of 45 degrees, and y is equal to x prime sine 45 degrees plus y prime cosine 45 degrees. And that's it. So this is how we're going to set up Excel, right? We're going to set up Excel to first compute A and B, the semi-major and semi-minor axes of that ellipse, in terms of the yield strength, which I'm going to leave the yield strength as just something you enter, right? And then, once we make that ellipse horizontal vertical, we're going to use these last two equations and tilt it. That's it, right? That's the cleanest way I could think of to do it. It does it in steps. One is make an ellipse, and two is rotate it so it looks right. Okay, so how does that even happen? Fortunately, I've got this page now, and now you can say, aha, he is doing Excel. Here it is, right? I'm going to use yield strength of 30 KSI, okay? Just picking a round number, right? It's pretty weak material, frankly, okay? A, we said was equal to the square root of 2 times, I'll pick on that SY number, and B we said was equal to the square root of 2 divided by the square root of 3. Yes, I'm aware I could have done that in one step. I didn't want to. I wanted to show it. Times, again, that number. And for the sake of making it look pretty, let me just knock down the decimals a little. Okay. Makes sense. We figured that long axis is bigger than the short axis. And for posterity here, I have the steps of what we're going to do. So now, I've already got the first line filled in for the coordinate transformation. That's just me getting out ahead of it a little bit. But you'll see that the equation for the coordinate transformation is x prime cosine of this 45-degree angle, right, which I have to do it in radians. If I'm doing it in Excel, I could convert to degrees. It's just easier to leave it as radians, minus the y prime times the sine of that 45 degrees, and y, the order's changed, but that's because I copy-pasted it over, is equal to y prime times the cosine plus x prime times the sine. Okay, that's going to work. All we have to do now is use that a cosine of theta and b sine theta equations. I've got thetas written out already. All I've done to get these thetas, I start from 0, and notice every step I go and I add 2 pi over 100. So when I get through about 100 lines of this, you see down here, this is 2 pi. Okay, 6.28, pi 3.14. Yeah, we're in the ballpark there, okay? So now, x prime is equal to a times the cosine of theta. Right, and what I'm going to do here, while I'm thinking of it, let's lock in that a. Okay, make sure that once I copy this down, it's not going to do something goofy. Y prime is equal to b times the sine of my angle theta. Okay, and let's lock in that b value. I'm putting dollar signs on both. I only need it on the row number, but I'm being super careful. Okay, notice the first thing that we get. We know that at that point, this point that I've chosen is really the point where x prime and y prime, where my two principal stresses have the same value, right? It's the 45-degree angle line, because I've gone from the tilted one, from the horizontal up to the tilted one. That means it should be sitting at sy, sy in space. It's sitting at sy. We're on to something here. Okay? I'm going to double-click the little button there, the little square, fill in everything, and I'm going to make it look a little prettier. Okay, so how do I know I've gotten this? Let's graph, which was the point anyway. I'm going to start off by plotting just the original ellipse. Okay, insert. I've highlighted the two columns. Insert chart. I'm going to pull this thing up a little ways, just so it comes up to where everything else lives, right about here. Okay, and I don't usually give these things titles, but we'll call it the von Mises Ellipse. Okay, so it looks okay. I mean, it's got the right shape, but again, it's not rotated by 45 degrees like we expect, but it's got potential. Okay, let's see how much potential it really has. Let's right-click on this guy. I'm going to choose Select Data. I'm going to add a second series. My x values, let's go in here, select a range, are going to go from D7 to D107. I'll accept that. My y values are going to go from E7 to E107. Yes, I could enter this manually, but the mouse is in my hand anyway. May as well keep going, right? So accept that one. Choose OK. Choose OK again. And that looks like we may have an ellipse. And to really see it, let's do two things. One, I'll go back to my Select Data menu, and I'll take that Series 1. I'm going to wipe that out. That's the first one I made. That was just the one that tested that I got an ellipse in the first place. And hello, huh? That looks pretty darned good. Okay, we've got this 45-degree angle point that's coming out and is making that show up at yield strength, yield strength. Our crossings of the coordinate axes are all sitting at the yield strength. We have ourselves a von Mises ellipse. Okay, and that's how we can draw this in Excel. Got a material with different yield strength. Okay, 70 KSI. And here's our new ellipse. No big deal. Okay, so again, our steps were first to draw an ellipse in horizontal and vertical axes, right? Using the parametric equation, x prime equals a cosine theta, y prime equals b sine theta. And then we rotated this to our xy coordinates, our coordinates where it's going to be rotated 45 degrees, using the equation I have here. X equals x prime cosine 45 minus y prime sine 45, and y is y prime cosine 45 plus x prime sine 45. And we have ourselves a von Mises ellipse. Okay, so there you go. Hopefully this helps. And again, thanks for the question. If you have any other things that you'd like to see, I'm finding that people really do like the Excel things, the little stupid Excel tricks I do. I think of them as stupid Excel tricks, but apparently they've got some use to them. Go ahead, let me know. Put something in the comments, and I'll see what I can do. Thanks a lot for watching.